Hi, and welcome to Mini Lecture 1 for Week 9 of the Quantum Universe for Educators. In this lecture, I'm going to run through an example calculation that demonstrates how you start from a quantum state of a system and then use that to calculate the probabilities of measuring certain outcomes. This is going to be quite similar to one of the calculations you are asked to do in question 1 from chapter 1 of Quantum Mechanics by David McIntyre. And the physical system that we're taking is our system of atoms that can be in a state of either spin up or down along one of the three Cartesian directions, and their spin components can be measured by the Stern-Gerlach apparatus that is either aligned with the z-axis, the x-axis, or the y-axis. And this is going to demonstrate the use of representing quantum states using Bra and Ket notation. Okay, so we're going to start off with a system described by a quantum state vector, which we're going to denote by this ket psi, and I'm just going to choose some arbitrary state, which is a superposition of up and down spin states along the z direction. Remember, when there is no subscript after these up and down kets, or plus or minus kets, that means that they're referring to the spin along the z direction, or the z component of the spin. In general, a quantum state will be some superposition of the up and down kets along the z direction, which means that it'll be represented, as shown here, by some coefficient that could be a real or complex number times the up ket plus some other coefficient, which could be real or complex, times the down ket. Now, I've just chosen the coefficients here arbitrarily. I've just made them up, and we'll see exactly what the meaning of this particular state vector is by doing the calculations. We have a real number in front of the up ket in this case, and a purely imaginary number in front of the down ket. And it's useful throughout all of this to have in mind a picture of a physical system that we are trying to describe to prevent everything getting too abstract. So we can picture, as in the original Stern-Gerlach experiment, that we are dealing with a very large number of silver atoms in a beam that is traveling along in some direction, and it encounters our experimental apparatus, our Stern-Gerlach apparatus, which will perform a measurement on these atoms, and it'll measure either the spin along the z direction, which you can picture as pointing up and down in the plane of this screen, or the x direction, which you can think of as pointing in and out of the screen, or the y direction, which you can think of as pointing left or right along the screen. Complementarity says that we can only measure one of those components at a time, and the uncertainty principle says that we can only ever have accurate information, precise information about one of those spin components. So we have to pick a spin component and measure it. We can't measure both the x component and y component of the spin at the same time. Now, before we get started, we have to check one very important thing. Any physical system, if it's going to be described by a state vector like this, that state vector must have one very important property. That is, it must be normalized. And that means the inner product of the state vector with itself must be equal to 1. Remember, the inner product is kind of like the dot product in vectors, but applied to this more abstract vector. And that has to be equal to 1. If we were dealing with ordinary vectors, then this would ensure that the vector was a unit vector. And the reason why we have to ensure this is because these state vectors, what they're used for is calculating probabilities of measuring certain outcomes. And the one thing that we know for sure about probabilities is that if you add up the probabilities of all possible outcomes, you have to get 1. Okay, so let's go ahead and check whether our state is normalized. So the inner product of this state psi with itself is just the Bra vector representing the state times the Ket vector. So to obtain the Bra version of this state vector, you turn these kets, these plus and minus kets, into plus and minus Bra vectors. The coefficients to and 4i now go behind the bra vector here. That's just the standard way it's written. And if any of these coefficients is a complex number, then you have to take its complex conjugate. And that just means you look at the complex number and you reverse the sign in the imaginary part. In our case, we only have one of the coefficients being complex, and it's actually purely imaginary, 4i, where I is the square root of -1. And so to take its complex conjugate, all you have to do is reverse the sign in front of the 4i. So that's why we have a negative sign here instead of a positive sign. Having done that, we can just multiply out the brackets as you would do an ordinary algebraic quadratic equation. So the plus bra vector times 2 is multiplied by the plus ket vector times 2. That gives you 4 times the inner product of the plus vector with itself, and so on. Now we can use the fact that these plus and minus bra vectors, as you've read about, form what is known as an orthonormal basis. That means they are themselves normalized, which means the inner product of one of these vectors with itself is equal to 1. So this is equal to 1 and this is equal to 1. And if you take the inner product of one of these basis vectors, one of these plus or minus vectors with the other one, you get 0. So these two terms are equal to 0. And then you note that in this last term here, the coefficient, because we multiply by minus 4i by 4i, you get minus 16i times I. And since I is the square root of -1, I times I is -1, and that turns this negative sign into a positive sign, and you end up with 4 plus 16 equals 20. So the inner product of this vector with itself is equal to 20 and not 1. So this vector isn't normalized, so it isn't suitable yet to describe the state of these atoms. But we can easily make it suitable because we note that once we've figured out the inner product of itself, of this state vector with itself, and it isn't equal to 1, then if we just take the square root of the number that we get and then divide the state vector by that square root, then our vector will be normalized. So we can go ahead and do that right now. So this is our state vector, which is normalized, the inner product of itself. The inner product with itself is equal to 1. So this is now suitable to describe the state of a bunch of silver atoms, for example, in a beam. Okay, so now we can go ahead and figure out what it means for this bunch of atoms, this beam of atoms, to be in this quantum state. And the meaning of any state you figure out by performing measurements on the physical system, on this beam of atoms in this case. And we have a choice of 3 possible measurements. We can measure the spin along the z-axis, the spin along the x-axis, or the spin along the y-axis. So let's start off by measuring the spin of these atoms along the z-axis. So we can schematically represent the experiment here. You have a beam of silver atoms coming along. It passes through this grey box here, which represents the Stern-Gerlach apparatus for measuring the spin along the z direction. And so what we know will happen is that this beam of atoms will separate into 2 different beams, one with spin up along the z-axis, and they will then be represented by the quantum state plus, and another beam of atoms with spin down along the z-axis, represented by the quantum state minus. So by making this measurement, this wave function psi has been collapsed into either the wave function plus or the wave function minus. So we'll get 2 separate beams represented by these 2 different quantum states. Now, no matter what the state is of these atoms, we will in general always get these 2 beams represented by these 2 state vectors. The thing that determines the meaning of this state is what the probabilities are for these various outcomes. So the probability of measuring one of these atoms with a spin up along the z-axis, a spin of +1/2, that probability is the square modulus of the inner product of the plus vector with the state psi, the initial state. And the probability of measuring the spins to be down along the z-axis is equal to the inner product of the minus state with psi squared. And if you converted these probabilities into percentages, then that would tell you the percentage of atoms that would be coming out in the plus beam versus the minus beam here. So in order to interpret what this state means, all we have to do is calculate these 2 probabilities. So let's go ahead and do that. So let's start off with the probability of measuring spin up along the z direction. First, we have to calculate the inner product of the plus bra with the psi state. So that is just equal to the product of the plus bra with this combination of the plus and minus kets, which is what psi is equal to. We're allowed to bring the plus ket through the coefficients here to give us this. So we have 2 over the root of 20 times the inner product of plus with itself, which is equal to 1, remember, since these states are normalized, plus 4i over root 20 times the inner product of plus with minus, which is equal to 0 because these states are orthogonal. So that just gives us 2 divided by square root of 20. So the probability is the square modulus of that. So if you take the square of 2 over root 20, you get 4 divided by 20. So that's 0.2. So that means if we measure a beam of atoms that are in this quantum state, 20% of those atoms will emerge in the spin-up beam. Okay, what about the spin-down beam? Well, now we have to take the inner product of the minus bra with the psi ket, which is given here. Again, we can bring the minus bra through the constant coefficients, and that gives us, for the first term here, 2 over root 20 times the inner product of minus with plus, which is 0, plus 4i over root 20 times the inner product of minus with itself, which is equal to 1. So that's going to leave us with 4i over the square root of 20. So now we have to take the square modulus of this to find the probability of measuring an atom with spin down. The previous square modulus was easy because the result was that we got for spin up was a real number, so we just take the square of that number. Here, there's a slight complication that this is a complex number. It's actually purely imaginary. So in order to form the square modulus of this, we have to take the complex conjugate of this number times itself. The complex conjugate you just get by reversing the sign in front of the imaginary part of the number. So the star here means take the complex conjugate, and so that means inserting a minus sign in front of the 4i. Multiplying these two numbers together, you get minus 16 I times I divided by 20. I times I is minus 1. So the result is 16 over 20, which is 0.8. So we can insert this here. So the probability of measuring atoms with spin down is equal to 0.8. In other words, 80% of the atoms you would measure coming out in the minus beam, the spin down beam. Now there's a very important check you should do when performing calculations like this, and that is you should make sure that your probabilities add up to 1. Physically, all of your atoms are passing through the detector, so 100% of them should emerge either in the top beam or the bottom beam. So the probabilities have to add up to 100% or 1. And here they clearly do. 0.2 plus 0.8 is 1. So that is good. And again, this emphasizes why we had to normalize our initial state psi. If we hadn't normalized it, these probabilities would not add up to 1. And then you'd get the nonsensical prediction that more than 100% of the atoms will emerge in one beam or the other. Okay, so this tells us that the meaning of this state, if a beam of atoms is prepared in this state, psi, then if you perform a measurement of the spin along the z direction, 20% of those atoms would be measured to have spin up and 80% spin down. What happens if you pick another direction to measure the spin? Well, let's choose the x direction next and see what we get for that result. So we know that if we start off again with our beam of atoms prepared in the state psi, pass them through a Stern-Gerlach apparatus aligned with the x-axis, then we're going to get the beam of atoms separated into two beams, this time with spin up along the x-axis, where we have the subscript here x to distinguish this from our previous ket, which meant spin up along the z-axis. And another beam of atoms with spin down along the x-axis. And we can write our probabilities of measuring spin up and down along the x-axis as the square moduli of the up and down bras along this x-axis with psi squared. Okay, to calculate this, we have to make use of the fact that is shown in the book that the plus and minus kets along the x-axis can actually be written in terms of the plus and minus kets along the z-axis in this way. So the plus ket along the x-axis is equal to 1 over the square root of 2 times the plus ket along the z-axis plus the minus ket along the z-axis. And the minus ket along the x-axis is 1 over root 2 times the plus ket along the z-axis minus the minus ket along the z-axis. Okay, so let's go ahead and calculate these probabilities. Let's start with spin up along the x-axis. So the inner product of the plus bra along the x-axis with psi is equal to 1 over root 2 times the product of the plus bra along the z-axis plus the minus bra along the z-axis, which is just the complex conjugate, which is just the bra version of this ket here, times the psi state written in terms of the plus and minus kets along the z-axis. So again, we can multiply out these parentheses just as we would do an ordinary algebraic equation. And we're going to get 4 terms. 2 of them will be inner products of the basis vectors with themselves, which will be equal to 1 in both cases. And 2 of these terms will be the inner product of one of the basis vectors with the other one. So plus with minus or minus with plus, and they'll be equal to 0. So once we get rid of the 2 terms that are equal to 0 and we insert 1 for the other 2 inner products, we get the final result that this inner product here is 1 over the square root of 40 times 2 plus 4i. So this is now a complex number. It has a real and imaginary part to it. So to take the square modulus of this, we need to multiply the complex conjugate of this number with itself. So let's go ahead and do that. So the complex conjugate of 2 plus 4i, which is written here as 2 plus 4i star, means, once again, that we just have to reverse the sign in front of the imaginary part of it. So instead of plus 4i, we get a minus 4i here. With that done, we can just multiply out these brackets, and we get 4 minus 16i times i. I times i is minus 1. So we get 4 plus 16, which is equal to 20. So our final answer for the probability of measuring spin up along the x-axis is 20 divided by 40, which is 0.5. So we can insert that up here. That tells us that 50% of the atoms should emerge with spin up along the x direction. We can calculate the probability that an atom will have spin down along the x direction in exactly the same way. The calculation is almost identical, except the minus bra along the x direction now has this extra minus sign here. We multiply out the square brackets again, insert 1 for the inner products of the states with themselves and 0 for the inner products of one state with the other state, and group the results together, and this time we get 1 over square root of 40 into 2 minus 4i. Taking the square modulus means taking the complex conjugate and multiplying it with the number itself. This time we have 2 minus 4i that we're taking the complex conjugate of. We reverse the sign and it becomes 2 plus. Multiplying this out, we end up with the result that the probability for finding an atom with a spin down along the x direction is equal to 20 over 40, which is equal to 0.5. So the probability, so that means 50% of the atoms will emerge with spin down along the x direction. Once again, we can check our probabilities add up to 1, which they do. Okay, so we split the beam exactly half and half. So we see that if we have a beam of atoms in a quantum state described by this vector, that means that we will measure 50% of them to have spin up along the x direction and 50% to have spin down along the x direction. To finish this off, let's look at the spin along the y direction. So this time we feed our beam of atoms with the state psi into Stern-Gerlach apparatus aligned with the y-axis. We'll get again a split into 2 beams, denoted this time by the kets plus with a subscript of y and minus with a subscript of y, and the probabilities are given by these formulas that should be becoming more familiar now. Again, we have to make use of the fact that the plus and minus ket vectors along the y direction can be written in the following way as combinations of the plus and minus vectors along the z direction. Note that these are very similar to the expressions for the plus and minus kets along the x direction, but with the addition of the imaginary number I in front of the minus ket here. So let's go ahead and calculate these probabilities. Firstly, because we now have an imaginary coefficient in these two kets, plus y and minus y, then when we form the bra versions of these state vectors, we not only have to turn the plus and minus kets into plus and minus bras, but we also have to take the complex conjugate of the complex coefficients here, which again just means reversing the sign in front of them. So the plus y bra vector will have a minus sign in front of the I, as opposed to a plus sign, which the ket version has, and vice versa. Okay, so let's start with the probability of finding atoms with spin up along the y direction. So the inner product of the plus y bra with psi is equal to this product here. We multiply out the square brackets again in a way that should be becoming familiar, and we again get 4 terms here, and we again can insert 1 for the two inner products of plus with plus and minus with minus, and we can insert 0 for the two inner products of plus with minus and minus with plus. Note that in this last term here, the coefficient is 4 over root 40 I times I, and I times I is minus 1, which turns this negative sign into a positive sign. So what we end up with is 1 over the square root of 40 into 2 plus 4, which is equal to 6 divided by the square root of 40. The probability is the square modulus of this, and that is easy to find because this is a real number, so we can just square it. So the result is we can insert up here the probability of finding spin up along the y direction is 36 divided by 40, which is 0.9. So that means that when we feed our silver atom beam in the state psi into the Stern-Gerlach experiment aligned with the y direction, 90% of those atoms will come out in the spin-up beam. Finally, let's calculate the probability of finding an atom with spin down along the y direction. Again, we can write the inner product like this. We can multiply out the square brackets, insert 0 for the plus minus and minus plus inner products, insert 1 for the plus plus and minus minus inner products. Note that 4I times I is equal to minus 4, so that changes the sign here, and we get 1 over the square root of 40 into 2 minus 4. So this inner product here is actually negative, minus 2 divided by the square root of 40. But again, the probability is the modulus of that squared. Since this is a real number, that means just squaring the number. Because it's a square, the minus becomes positive, and the probability of finding atoms with spin down along the y direction is equal to 4 divided by 40, which is 0.1. So 10% of the atoms that we feed into our y Stern-Gerlach apparatus come out in the spin down beam. And once again, 10% plus 90% is equal to 1. Our probabilities add up to 1. That means we've done the calculation correctly. You should always check your probabilities for possible outcomes add up to 1. That is a sure way of checking that you've actually done the calculation correctly. If they don't add up to 1, then something has gone wrong somewhere. Okay, so to summarize, we've done a sample calculation which illustrates what a quantum state means, or how to figure out what a quantum state means practically or physically. All right, we have these beam of silver atoms prepared in the quantum state psi is equal to 2 times the up state along the z direction plus 4 times I times the minus state along the z direction. And what this means is revealed experimentally by performing measurements. And we have performed 3 of the simplest measurements that we could think of here. If you feed this beam of atoms that are known to be in this state into the X Stern-Gerlach apparatus, then you'll measure spin up with a probability of 50% and spin down with a probability of 50%. If instead of X they pass through a Y Stern-Gerlach detector, then you'll measure 90% with spin up and 10% with spin down. And finally, if you feed the same beam of atoms in the same quantum state instead of X and Y through a Z Stern-Gerlach detector, then you'll measure spin up with a probability of 20% and spin down with a probability of 80%.